Hello everyone, welcome back to the Keras tutorial. So in the last tutorial we saw how to install Keras and how to install TensorFlow, import Keras and TensorFlow, and then we saw basics of how we can use Keras and then what some of the things we can use in Keras. So in this tutorial I'll be talking a little going more in the sequential API and how to use that. So to do that I have made this notebook. So we'll be using the NumPy module to make the an artificial data, and from Keras we'll be importing the sequential API. This is how we can import this, and this we can also import a functional model, which I will be taking up later. For this exercise I'm only working with a very simple neural network model with just one dense layer followed by the output layer. What happens is, for a neural network model we need to convert the Y or the output to a one hot encoded vector. So as we saw like last time, if we have like three classes, then let's say if we have three classes 0, 1 and 2, then let's say the first is for each of these will be let's say the first one is the 0th, so it will 1 0 0, and let's say if the second row is basically again the 0th class, it will be again 1 0 0. So let's say third row is basically the second class, so it will be 0 0 and 1, and this is basically the one hot encoding. So let's and then I'll be using matplotlib to plot some we'll be plotting the loss and accuracy and the time taken. So let's import this thing. So it's now using the TensorFlow backend like we saw like last time. I also imported from last time two other modules, matplotlib and seaborn, for plotting the graphs. And if someone has to see what the command was, this is the command that I used. Then basically I will be generating a data with 30,000 rows and 1,000 columns. So this is basically what we can use here, and we will have like 50 classes here, or we can, let's say for this exercise, let's say we just have 20 classes. In the validation set we will be having 25% of the data, so we will train on the training set and validate on the validation set. The batch size is basically how many rows will be considered per before a change is made in the weights. Using the gradient descent, and I'll be talking more on a gradient descent later maybe. Then the number of epochs is 3, so how many passes over the data the neural network will be making, so 3 passes. And then verbosity is basically with how much output should the neural network just go. It's basically showing the progress bar of the neural network model. And neurons is basically how many number of neurons we'll be using for this task. Now let's generate the data, and as we had provided, it has the 30,000 rows and 1,000 columns, and 30,000 rows and 20 columns, because what we did is after generating the data we converted it to using the two categorical to a one hot encoded form, and this is the input that Keras takes. If we don't do this, we will be getting an error, so make sure that this needs to be done. This is the step that converts a vector to one hot encoded vector, and this is necessary. An additional step is to shuffle so that we don't have any kind of bias. Now we generate a train and a test set using the validation split we had considered earlier. And just to give an idea, for example, this is how our y has been transformed now. We have 20 classes, so 0 1 2 3 4 5 6 7 8 9 10 11 12. So this is the basically the class number 13, because it is on the 12th to 12th position, and all in all there are like 20 values in this thing. For the model, it's quite a simple model, as I had said before. We will first initialize a sequential model. It's very simple to do that, and then we add the first layer. The first layer is basically the dense layer. It takes the input neurons. Now this input is basically, it can be also given as output dim. So how many rows of output should be, this will be given. So if we look at fully connected neural network, then we will understand that what I'm going to talk. It's basically the input dimension is this and the output dimension is this. So basically how many connections has to be made to the next layer. So it's important, so and it's a required thing. The input dimension is basically how many rows, how many inputs should we expect, and this is basically the X train shape 1. So X train shape 1 is basically nothing other than 1000. So basically although we have 22,500 examples, but it's row by row, so but it will pass in number of batches, and we define the number of batches here, the batch size 128. So every time time it will be like 128 rows, but the number of columns will 1000. So we need to provide that, and we need to provide this only for the first layer. For the others layer, Keras is smart enough to understand itself. For the initialization of the weight, so as we saw here, this is each of these is a weight matrix, and how it will be initialized is basically it will be initialized using a random uniform. There are other ways of initializing as well. So for example, we can initialize to 0, we can initialize to 1s, we can initialize to a constant value, we can initialize to a random normal, we can initialize to a random uniform, truncated normal, and so on and so forth. So there are multiple initializers, and for the kernel and for the bias. So for example, when I'm going to talk about the convolutional neural network, then the kernels will come, and then we will also have the bias. In those terms, it will be very, very important. For example, right now I have my kernel, then I basically add a final output layer, and this basically, let's I had uniform initialization, let's say make it random uniform here as well, and activation here has to be softmax, it cannot be anything else. Why is basically, let's say we have the 20 classes. Now each of these 20 classes, like we'll talk last time, will have some probabilities, and they have to add to 1, and whichever has the highest probability, we will say, let's say this is 0.6 and the rest others add to 0.4, we will say that this is the class that it should be assigned to. So that's why it has to be softmax. And the loss is basically the mean squared error here. There are other loss functions as well. So there are multiple loss functions like mean squared error, mean absolute error, mean absolute percentage error, mean squared logarithm error, squared hinge, and so on and so forth. Mostly for a multi-class problem, we use a categorical cross entropy, and for a binary problem we use a binary cross entropy, and those perform good. I'll be doing some experiments where we can see how the different losses perform. Optimizers is right now I'm using the SGD, this stochastic gradient descent. There are other optimizers as well. So for example, SGD, we have stochastic gradient descent, we have RMS prop, we have ADA grad, we have ADA delta, we have ADAM, we have ADAM max, and we have NADAM, and so on and so forth. So you can see the maths behind the different loss functions here. So for example, the mean square error, the loss is defined as basically yi minus y pred squared sum divided by the total number of observations. So for each observations, what was the true label and what is being predicted, the difference between that squared, and this is done for all the observations that we see. Mean logarithmic error is basically log of the actual class plus 1, log of y actual plus 1 minus log of y pred plus 1 whole square divided by total number of observations. We also have the L2 norm, the mean absolute error, and so on and so forth. This is basically what I will be using, the categorical cross entropy. So it's basically summation of y log y true log y pred plus 1 minus y true into log of 1 minus y pred, and y true is basically the actual label of the class, and y pred is basically what is being predicted, the probability between 0 and 1. And in most of the cases, cross entropy will work the best, and that's what I'll be using mostly. Metrics is basically what we want to track. This is a list, and you can apply different things. We can add different things here in this. So let's run this, and as we see, basically we have a very simple model with two simple layers. The first is dense layer and second is dense layer as well, and this has 330,000 parameters. These are 620 parameters, and total parameters is 30,650, and all of them are trainable parameters, and there's no non-trainable parameter here. To fit a data, so once we initially compile the model, the next step is basically to fit the data. It takes the X train, the Y train, and the Y train again has to be in the one hot integrated format. What is the batch size and the number of epochs for each it has to be done, and the verbosity that we defined above. So as soon as I press shift and enter, this cell will run and this will start training. So what this shows us is basically this is the first epoch, and the first epoch is it went through all the training examples, so all the 22,500 examples that we had in training set. It went through all of it, and what it found was the loss was this and the accuracy was this. Now this is a simple made up example, so we do not worry much about the loss and the accuracy. We are just trying to learn on data. Later when I'll be using the MNIST data set, we will be trying to improve these scores further. This is just to give an idea that this is how we can train our Keras model, sequential model. Now as we can see, there are multiple things that we can change here. If you come from the machine learning background, then scikit-learn has something called grid search CV, which is basically used sometimes to tune the parameters and get the best parameter set, because parameters sometimes can be really important. So let's say what happens, one of the changes that we can do is increase or decrease the number of neurons in the hidden layer. So let's say if we try to do that, let's say what happens. So what we are doing here is for each of these number of neurons, we are training a model, and then we are getting the same accurate loss and accuracy metric. So what we can see is initially when I had just 20 neurons, the accuracy was 0.45, and now the accuracy basically kind of a little bit decreased to 0.515. But when we went to 100, the accuracy increased to 0.0656. So in a way, shortcut to defining how many number of neurons we should be using, but a rule of thumb is if the data is more complex, obviously we need more number of neurons, and the number of neurons basically reflects the number of weights we have in the model. And the more complex the data is, or the more complex data is, the more number of weights we'll be needing in this. So that's why in those cases the number of neurons should be increased. But oftentimes what will also happen is if we increase the number of neurons to a really high number, then the model might start to overfit. So in that case, we would like to control these number of hidden units. So let's plot this now. So what we see is basically the loss and the accuracies don't change by much. As we can see, it's a flat line. However, the time in microseconds is basically quite fluctuating. So as we can see, I think it's for 50 neurons we have quite number of the least time, so we'll be using 50 neurons from henceforth. So what we can also do is basically trying to use more number of epochs. So let me change the number of neurons to 50 and then run this thing, so that now number of neurons is 50. For the number of epochs, what I have done is basically we can now train on 3, 10, 20, 50 and 100 epochs and see how the losses, accuracies and time taken change, and then plot them. Obviously the more number of epochs, the more time it will take. So for example, for just 3 epochs it took 32 microseconds per step, which is quite fast, but for more epochs it will take more time. Again, what will happen is, if we look at the training and validation accuracies, it will the loss will decrease with the number of epochs, but again after some time it will start to plateau, and we don't want to go beyond that, because the more number of epochs, the more time it consumes. It will kind of increase, the time taken will increase exponentially. So we need to be mindful of how many number of epochs we do, and there are ways of doing early stopping, which I'll be talking later in the course. What that will do is basically, even if we give a high number of epochs, it will automatically stop training if there is no significant change in the validation accuracy after a certain point of time, so that we can save precious time. So as I'm just training on the CPU, and this will take a lot of time. It's training the last epoch, and it's now it's training on the 100 epochs, and now it has done 75 out of them. And you can see that in all of these epochs it's training on all this training data, but the batch size was 128, and the weights for these models, so for each of these weights, are being changed only after training has been done on one batch size. So I think we have trained all of it. Now let's go and plot them. So what we see is basically the one in orange is the accuracy, and the accuracy peaked around the epochs at 50, and we can see the time also is the maximum there. So for now we'll be so the another way to do is, now we should be training at 50 epochs rather than 3 epochs that we had before, because that's basically under training. Another thing we can do is basically try to choose the different loss functions. There are multiple loss functions that we saw. We can use it here. There are either we can use it like this, or we can import import this and then initialize it with different values. For example, so now let's do that. So number of epochs I'll be doing, let's say the 50 that we found out before, and now what it will do is for each of these loss functions it will train on each of them. So now we're compiling on this. So basically for each of these steps we have a new loss function. The optimizer for now is the SGD. We will be also looking at iterating on the optimizers in the below, and the metric that we are using right now is accuracy again. And what I'm doing is I'm getting a start time, fitting the model, and then getting loss and accuracy on the evaluation or the tests or the validation set that we want, and then we are getting when this is ends, and then we are adding all these values here. So this is still training, and this will take a significant amount of time because we have so many we have like 13 or 14 loss functions, and for each of them will be trained on 50 epochs. This is basically just to see which of them perform the best. I will suggest if you are using multi-class problem to go simply with the categorical cross entropy, and if binary problem is being solved, to use the binary cross entropy, which more often than not will be the best choice out of there. But again, it's a good idea to experiment because then depending on what needs to be done, that might change. Also what you can do is you can define your own loss function. So I pretty much believe Keras gives that an option. So we can use I will be looking into that later. So I will pause the video for now, and then when this is done I will come back. So hinge, it's doing hinge now. It has to do 1 2 3 4 5 6 now. So this is done, and I've already plotted it. As we can see, the mean absolute percentage error has the highest loss, and the others are almost the same, as since the data is really artificial. It's not, and the mean squared error has taken the least time. So it's actually does not give any insight, but on actual data this might give a better insight, because then the fit will be much better. The next is basically on how to on the batch size. So we can try to change the batch size. So, and a batch size is basically after these many number of examples being seen, a change will be made to the weight. And here I'm using categorical and cross entropy. Optimizer is still the SGD, but now we'll be changing the batch size. So with 32 batch size and 50 iterations, again it will take some time. What I will do is basically I'll pause the video again and then come back when this is done. Again it's done now. So as we can see, as we increase the number of batch size, the training time decreases, and this makes sense because as we increase the batch size more and more, then more data is being used at the same amount of time. We can also do the same with optimizers. So we have different optimizers that are available with Keras. What we can also do is basically for each of these we can either give a string, or we can initialize this to a variable and then pass that. With string, it will take the default values it has. If we want to change, let's say, the learning rate or the momentum or the decay, then, or we use the nester momentum or not, this can be changed by initializing this to a variable and then using that. So I'm just using training for 3 epochs, because even if I go for 50 epochs, it won't change much, but if we go for 3 epochs, the training will be much faster, and then I won't have to pause the video again and again. As we can see, there's not much difference, but the adder grade apparently takes the least time in training, and the Adam optimizer takes the maximum time. The same can be done for the activation functions. There are multiple activation functions available. The softmax needs to be used always in the outermost the output layer, and there are like elu, celu, relu, soft plus, softline, tanh, and sigmoid that can be used. And this, I found this tutorial basically. So for example, the linear activation function is basically y is equal to x. Since what we're trying to do is we're trying to find a function, a non-linear function, to fit this data. So the idea of neural network is to use a function so that can behave like a non-linear function. So we can use something like a sigmoid, or this is also same as logistic function. This is the S-shaped curve, and basically the fx is 1 by 1 plus e to the power minus x. We have the tanh, and tanh is basically we can see it also goes into the negative y and x axis. This is this is less steep as compared to the sigmoid here. And the relu is basically y is equal to x when x is greater than or equal to 0. So basically, in short, it can be summarized as r of z is equal to max of 0 of z. So whenever it's in positive quadrant, it will be always behave like y equal to x, and whenever it's like less than in the negative quadrant, it's like 0. And at this point, the function is not differentiable, but the differentiate and all these functions needs to be differentiable, but at this point we consider the value to be 0. We also have for the leaky relu, basically there's a small deviation, so it's that. And then we have also p relu and so on, others. Mostly people use relu, and that's one of the most used for the activation functions for the middle layers. P relu also can be used. It's one of the advanced activation layers, which can be accessed from here, and from keras.layers.advanced activations we can import the p relu and leaky relu. I will suggest reading the papers regarding all this. So it's stating for 10 epochs, and it will take some time. I will pause the video, and then once that is done, I will be putting it back again. So for example, with softmax, we can see we got the accuracy of 0.0653. For elu, we got accuracy of 0.1161. So we can see that changing the activation function actually has some effect. Again, we can see using celu has decreased the accuracy a little bit. Again, no meaningful insight has come here, but then the idea is basically there are a lot of things to tune in this neural networks. It's not like we just instantiate it and run it and then it runs perfectly. Most, like for example, the activation function can value the loss function. I try to use one of RMS proper Adam, but you can experiment with others, and we can the optimizers, and within the optimizers there are some variables that can be changed, especially the learning rate, and these can actually have an effect on the accuracy and on the accuracies. So this tutorial was given an idea about the Keras sequential example, and hope you liked it. I'll be putting up more tutorials on Python, Keras, machine learning and deep learning. Please subscribe to my channel. Thank you.